Hi everyone, I'm Milind from Carnegie Mellon University, and today I'm going to talk about our work Pryde on uncovering evasion attacks against stateful firewall deployments. So let's say you're a network operator who wants to protect their internal hosts from external adversaries on the internet. The natural thing to do here is go online, find a reputable firewall vendor, and deploy their firewall in front of your network. You're probably going to configure it with some rules such that external attackers are not able to access your internal hosts. However, even in such a case, an attacker out on the internet who has no access to your firewall code or the firewall rules can actually exploit subtle bugs in the firewall's packet processing logic and evade the firewall's defenses and ultimately attack an internal host. So let me give you an example of a concrete deployment scenario where this can happen. So we have the LAN and the WAN separated by the firewall. The attacker is a host on the external network, which can craft and send any TCP packet destined towards an internal host. There's a critical victim server lying inside the internal network. This critical server might be running an old OS and might have a vulnerability, but is being expected to be protected by the firewall. The operator configures the firewall with the correct rules. So a canonical example of rules that are configured is that TCP connections should only be allowed from the internal to the external network and anything else should be dropped. There might also be an insider threat in the network. So this insider might be a low security IoT device that has been compromised by the attacker using an attack such as Mirai. Now, because the operator is security conscious, they kept their critical victim servers in a different VLAN. So the insider cannot observe the victim or cannot send packets to the victim. However, this insider can spoof packets as the victim and send them towards the firewall. So with this deployment scenario in mind, let me show you an example of a concrete evasion attack that was found by Pryde, where the victim host is running an older version of Ubuntu, and the firewall here is an actual concrete firewall, which has been anonymized as Firewall 2. So the attack starts with the insider sending a spoofed SYN packet towards the firewall, which punches a hole in the firewall's defenses and allows the attacker to send a SYN packet towards the victim. The victim responds with a SYNAC packet. The attacker just then, to confuse the firewall, sends a SYNAC packet back to the victim, which then responds with a reset packet. Now, at this point, given that there's a reset packet been sent, you would expect that the firewall would not forward any more packets between the two hosts, the attacker and the victim. However, the attacker is actually able to send malicious TCP data through to the victim, which then also responds with an ACK. And this is an example of a successful evasion attack. So now that I've shown you what an evasion attack looks like, let me tell you why it's challenging to find these attacks. So the first reason is that of black box access. So the attacker has no access to the firewall's code base or what rules the operator might have configured in the firewall. Secondly, there's a vast variety of firewalls that are present out on the marketplace. And obviously, finding an evasion attack depends on the exact logic that the firewall is using to process the TCP packets that are sent towards it. Thirdly, there's also a large variety of hosts that can exist in the internal network behind the firewall. These hosts might have different operating systems, different networking stacks, and there might also be different kinds of insider threats. And any framework that is trying to find evasion attacks must be able to account for the interactions between these different hosts and the different firewalls that might be present in front of them. So now that I've told you about challenges in finding evasion attacks, let me quickly go over why prior work is ineffective at finding these attacks. So there are works on firewall rule testing that test the rules that operators have configured in a firewall. However, they do not test the actual behavior of the firewall in response to these rules, and they obviously require white box access to look at the firewall rules. There's a whole bunch of work on censorship circumvention. However, these attacks are ineffective when generating attacks against firewalls because firewalls often use stricter default drop semantics. Code analysis tools require white box access to code, which is why they're not practical. There are works on protocol fuzzing as well that are able to fuzz different network protocol implementations. However, they assume a very simple client server model and are not generalizable across different kinds of deployments, such as those with insider threats. There's also a class of work on automata learning. However, they do not model the firewall response to non-TCP compliant packets, which are exactly the kind of packets that we need to generate evasion attacks. So now that I've discussed some of the prior work, let me tell you how Pryde is able to solve the challenges in finding evasion attacks. So Pryde's first insight is the following. Instead of looking at only the firewall in isolation, as some of the prior work has done, Pryde takes a deployment-aware approach, where it considers the firewall and all the other facts of the deployment, such as the fact that the insider can spoof packets, or the insider cannot communicate with the victim, etc. And it considers all of these in conjunction to try and find evasion attacks. Now, unfortunately, naively reasoning about the entire deployment along with the firewall results in scalability and extensibility issues. So, for instance, if you want to reason about a particular deployment with a new firewall, you would have to run the entire workflow again. So, to take care of this challenge, Pryde actually takes a modular approach where it decouples analysis of the firewall from analysis of the deployment, which allows it to be scalable as well as extensible. Now, in reasoning about the firewall itself, one can either take a model-free approach or a model-guided approach. So model-free approaches are those such as fuzzing or genetic algorithms, and while they're useful, they're not able to model the subtle bugs that may be present deep in the firewall logic. And so Pryde takes a model-guided approach where it infers a set of finite state machines that models the behavior of the firewall. So let me give you an overview of what the Pryde workflow looks like. So so Pryde takes a black box firewall appliance as an input, which is given as input to the firewall model inference module, which then produces a firewall model using only black box access. Given this firewall model and a model of the deployment of the network deployment, the symbolic attack generator generates a set of symbolic attacks. So each symbolic attack is an abstract representation of a TCP attack in some high level space. Now, uh, when we actually have to play these attacks out on the network, we cannot deal with symbolic attacks. We actually need concrete precaps that can be played out on the network. And that's exactly what the concrete attack generator does. So before I describe all of these three modules in detail, let me show you how an operator would actually use Pryde in practice. So this is the interface that Pryde provides to an operator. So first, the operator just needs to specify the network configuration, so the firewall IPs and the subnets and IPs of different networks that are present. Secondly, the operator needs to specify the deployment model. So for instance, this is a description of the deployment model that in which I described the evasion attack. So for instance, the insider resides in the internal VLAN 2 network. It can send a packet with its own source IP or the victim source IP, which is the spoofing part, and it can send a packet destined towards the attacker. Um, Now, the operator also has to specify an attacker goal, which consists of two parts: an SMT constraint that is used during symbolic attack generation, and a success criteria, which is what the final attack PCAP is tested against. So if it satisfies the success criteria, it's considered a successful attack. And the last is a victim model that the operator could give as input. Pryde has a bunch of victim models built in, but the operator could also specify their custom victim model. And this is just an approximate model that helps Pryde prune the search space and find more targeted attacks. So Now, here's the first part of the Pryde workflow, which is firewall model inference. So the inputs here are a black box firewall appliance and an input alphabet, which describe the set of packets that can be sent to the firewall. And the output here is a firewall model. Now, naively reasoning about the firewall appliance in the face of all kinds of adversarial or evasive TCP attacks leads to scalability issues. And so Pryde's key insight here is to consider different input alphabets, each which encode a different kind of evasion capability, and Pryde infers an ensemble of firewall models. So this is an example of what an input alphabet and a corresponding output model looks like. So the input alphabet would define a TCP packet with a certain TCP flag and a certain direction, such as a SYN being sent from the internal network to the external network. And the output model would describe state transitions between different states when the firewall encounters a certain packet, and it also describes the firewall's output in response to a certain packet. So the firewall might forward a packet to its destination host, or it might drop the packet. So given this ensemble of firewall models that have been generated, the symbolic attack generator takes these models as input, and it also takes certain facts about the network deployment as well as the victim model that I specified earlier as input. It converts all of these to SMT constraints, and then it considers the attacker goal that has been specified by the operator, feeds all of these to an SMT solver, and generates symbolic attacks. Now, naively generating symbolic attacks can result in a lot of repeated symbolic attacks, which are encoding the same conceptual capability of the attack in evading the firewall. And so Pryde's key insight here is to add a constraint which generates semantically distinct symbolic attacks. And the bottom right here shows an example of what a symbolic attack looks like. So it's a high-level representation of a sequence of TCP packets, just specifying whether there's any data present in the packet, what the TCP flags are, and the sender and the receiver of the packet. So given a set of semantically distinct symbolic attacks generated, the job of the concrete attack generator is to generate. So given the set of symbolic attacks that have been generated by the symbolic attack generator, the job of the concrete attack generator is to set sequence and ACK numbers for each packet in each attack so that we get concrete PCAPs that can be played on the network and tested against the attack success criteria. Now, setting sequence and ACK numbers by exploring the entire space of sequence and ACK numbers is prohibitively expensive. And so, on the other hand, if you actually try to set sequence and ACK numbers with a very strict dependence between the packets, you actually don't explore a large part of the sequence and ACK space. And so our insight is to maintain a loose dependence between the sequence and ACK numbers of different packets. And so what we do here is we use some heuristics to generate a dependency graph where each node is a symbolic packet and an arrow between two nodes denotes a dependency of one packet's sequence and ACK number on the other packet's sequence and ACK number. We then prune this dependency graph to a spanning tree and use a set of heuristic strategies to generate these concrete attacks. So one example of a heuristic strategy is a TCP compliance strategy, which tries to maintain TCP compliance in assigning sequence and ACK numbers to different packets. An example of a baseline strategy is a random strategy, which just assigns sequence and ACK numbers randomly. Another strategy that we use is a delta step strategy, which assigns sequence and ACK numbers to a packet based on the previous packet's sequence and ACK number plus a certain delta amount, such as 1 or 2 or 10. So at the end of this workflow, we actually have a set of concrete PCAPs that can be played out on the network and evaluated for success. So to evaluate Pryde, we take four popular commercial firewalls. One of them is open source, three of them are closed source. For each of the firewall, we have 10 input alphabets that we use to generate 10 models in a black box manner. For each of these 10 models, we generate attacks against four diverse victim servers. So a Contiki OS, which has a telnet server, TTY Linux with an HTTP server, and two older versions of Ubuntu with Netcat servers. So Pryde is able to find attacks against all of these four commercial firewalls. And here attack success is defined as the attacker being able to send malicious data to the victim and the victim responding with a TCP ACK. Prior work and strawman solutions are actually ineffective at finding attacks against any of these firewalls. Now, if we actually make the success criteria more strict and have the criteria that the TCP ACK from the victim must actually be forwarded back to the attacker, Pryde is still able to find the same number of attacks against three of the firewalls listed over here. And this sort of an attack gives the attacker feedback about whether their attack was successful or not. Now, if you recall, I talked about firewall diversity as one of the challenges in generating evasion attacks. And so to quantify this, we asked the question, can successful attacks against one firewall generalize to another firewall? And we found they cannot. So this is a simple heat map that shows what percentage of concrete attacks that are successful against one firewall on the x-axis um, generalize or are successful against a firewall on the y-axis. And so clearly the attacks here are per firewall. In fact, if we do this exercise with symbolic attacks, even then we notice that only a small percentage of attacks that are successful against one firewall are actually successful against another firewall, reinforcing the need for a framework which generates attacks that are custom or are tailored to a certain firewall. So in the process of finding these attacks, Pryde also finds some cool idiosyncratic firewall behavior. So one behavior that we notice is that firewall 1 proactively spoofs reset packets and sends them to hosts. And we think this is a reason why Pryde found very less number of attacks against firewall 1. On the other end of the spectrum, firewall 3 allows an ACK in any direction without any preceding SYN packet, which was very surprising. And we think this is the reason why Pryde discovered a whole lot of attacks against firewall 3. A common theme that we notice in all of the different firewalls that were tested is that even after a reset packet has been sent, the TCP connection state is not teared down, and the firewall still allows packets to go through from one host to the other. So I'd also like to share some anecdotes from the vulnerability disclosure that we performed. So for firewall 1, the vendors asked us to test our attacks against a newer version of the firewall. And we noticed that this newer version is actually more aggressive in spoofing these reset packets, which thwarted some of our attacks. Firewall 2 vendors acknowledged our initial report, but did not follow up with us. Firewall 3 actually enabled a default setting in their configuration to enable, which enabled strict TCP session handling, which actually thwarted some of our attacks. And Firewall 4 vendors also asked us to test our attacks on a newer version of their firewall, and we found successful attacks against the newer version as well. So while I've painted an extremely gloomy picture here of Pryde being able to find evasion attacks against multiple different firewalls, the way that we see this is that operators and vendors alike can use Pryde to proactively test firewalls in different networks, and vendors can definitely use such a system to evaluate firewalls before and after patches to ensure that evasion attacks have been patched and no new attacks have been introduced. So some quick takeaways from my talk. Firewall security can be evaded by subtle bugs, and it's extremely challenging to discover these evasion attacks. Pryde offers a novel capability to operators and vendors to systematically discover evasion attacks against different firewalls. It's able to customize these attacks and tailor these attacks to different firewalls and deployments. And in the process, Pryde also finds idiosyncratic firewall behavior. That's all. Thanks for listening, and please feel free to contact me if you have any questions.